Please welcome Jing Xiao.
Thank you, Mark. Thank you for this opportunity. I'm very pleased to be able to have an in-person kind of gathering and to make a presentation. So today I'm going to talk a bit about my group's research related to robot perceptions, action synergy, and certain environments. We know that when a robot works in an unknown or uncertain world, it requires sensing and perception to guide its motion. But often, action of the robot is also required to further facilitate perception and action. Sometimes the action itself is for perception, acts as a means for perception. So we're interested in combining perception and action to solve problems for a robot to accomplish many tasks. I'd like to talk about 4 areas of the research. The first is robotic assembly in the presence of uncertainty, then autonomous object modeling and recognition, real-time adaptive motion planning in uncertain environments, and semantic SLAM in unknown environments. Robotic assembly is a long-term problem. The main challenge is how to deal with tight tolerance with large motion and sensing uncertainty of a general purpose robot, which can result in parts forming different kinds of contact states. So this is a long-standing problem. Research has dated back to the 1970s even, but mostly focused on some packing hole operations and classical approaches, including using a passive compliant device or active compliance by doing contact state detections and compliance transitions using compliant control, force, or impedance control. There's a big body of work related to that. And more recently, learning-based approaches. Learning is a very promising tool for means for a lot of tasks that has uncertainties, a lot of variations. So people use learning by demonstration or reinforcement learning and so on. But still, the approaches are limited mostly to task-dependent specific cases, a particular kind of assembly operation, or in the general sense, it's a simple shaped single packing hole assembly. So general assembly of complex shapes of parts, such as multi-packing hole assembly tasks, remain an open problem. We're interested in autonomous complex assembly with a general task independent approach. As shown here, if we have a double packing hole assembly operation, and then due to the uncertainty between the pack and the structure and the whole structure, multiple region complex contacts can be the results. And to overcome uncertainty, we have to overcome these kind of unintended but complex contacts configurations. So we consider the general problem as having 2 parts, a P and H. I say pack, but doesn't mean a single pack. So I say a pack structure and the whole structure, P and H. And the one key thing is represent those parts in a relatively geometry shape independent fashion. We use a sphere tree representation. So it's a hierarchical representation, but it's all using spheres. Here, this is the last level or the lowest leaf level spheres representing the pack structure and the whole structure. This is just one example. It's actually the octree, but we use more efficient sphere tree representation methods now. But the whole idea is when we do that, just like one can use a triangle mesh to represent all kinds of shapes, all kinds of objects, using this kind of sphere structure, we can have solutions for this assembly problem that's kind of independent of the particular geometrical shapes. And we consider nominal motion. In this case, is just a straight line insertion motion with no uncertainty considered. But we definitely consider 6-dimensional position and orientation uncertainty of the pack structure relative to the hull. And we use force torque sensing. In this case, we just use force torque sensing. So the whole approach starts by having the robot command the pack structure along the nominal motion to the whole structure. And because of uncertainty, some contact like this, some kind of contact will be detected at force torque sensing, but we don't know what kind of contact, right? So we predict the uncertain pose of the peg with respect to the whole structure, but the prediction may not be an actual contact configuration. Contact configuration is much harder to achieve. So we start from this, cannot see very much. Okay, we start from this kind of a predicted pose. Then we need to compute the corresponding contact pose. And this is inspired by some approach of haptics as interaction simulation. And then use the contact pose computed to compute the force and torque related to the contact configuration. But then this computed force torque is, of course, subject to all kinds of model simplification and inaccuracies and so on. So we further calibrate this to a sense force torque. And this is a learned model. This is also a crucial step. And then the output of this model is matched to the actually sensed force and torque in this situation. If they match, we say the computed contact pose is accurate enough with the computed uncertainty, and we can update the goal state of this assembly operation, and then command the robot commands the peg structure to the update the goal configuration compliantly, and that to reduce uncertainty and to be successful. And if not, if this computed force and the sense force do not match, we'll do this again. This whole process starts again. So now, if we are given just some kind of pose of the peg with respect to the hull, it can be something that causing interpenetration, like this gray part, the gray peg structure and the hull. So we need to find the actual corresponding contact because we are assuming, not just assuming, that actually the parts are rigid. So we do that through constraint optimization, avoid penetration, and minimize the potential energies. So-called potential energies, we assume there's a spring connecting the previous pose or the gas pose and the contact pose. And I try to find the contact pose that minimize this energy and avoid penetration, so subject to this constraint. And after solving this constraint optimization problem, we have this contact pose. And we can compute the force by Hooke's law. Just want to mention that contact constraints become much easier to formulate in a general uniform way because of the sphere tree model. So this is one major reason why we do this kind of representation of objects. So this just shows some example. And we have a 2-peg hull case. This is nominal motion doesn't work. Next, you can see we detect the contact or predict the uncertainty and find the contact configuration and find the force matching and update the goal configuration and then compliantly move the peg to the goal configuration. And this is successful. But this, in this example, this is actually earlier work. This example only considered 2 orientation uncertainties along the roll parameter and pitch parameter. And you can see the robot doesn't know this uncertainty, even though we have the ground truth. the predicted uncertainty, and this is a different case, predicted uncertainty and can be a little bit far from different from the ground truth, but still this is a much better prediction. And with compliant motion, the transition can be successful. This work is still a little bit slow, you can see, but later on I'll show you another example. We have speed up quite a bit with making the procedures, a lot of these procedures much more efficient. Okay, so this is, I think, it's repeating now. So, no, missed something. Sorry. I'm going to show just quickly a 3D case. Not 3D, sorry, a 3-hole case. Okay, so we also have the 3-hole case, but in this, the arrangement holes don't have to be like that, can be really arbitrary. It doesn't matter. The holes can be different and the arrangement can be arbitrary. So the whole thing still works. I'm not sure why this is stopping. Hope it's okay. Just quickly see that. Okay, so more recently we consider these sharp peg and holes, and in this example we have 2 triangular peg and hole, and the same kind of exactly the same strategy, but we have a much more efficient implementation. You see, this is much faster than the previous one. And also in this case, we consider 6-dimensional uncertainties, 3 positional and 3 orientational uncertainties. And still, the method can be fairly fast comparing to the previous case, previous implementation. You can see sometimes the first prediction may not be able to lead to a successful prediction or estimation of a contact pose, and then the whole procedure starts again. And you can see on the left side, sometimes it has to do a second attempt of the prediction, but still the task can be successful. This is actually a 4-pin mixed shape pegging hole task. It goes pretty fast, but the 4-pin of the different kind of shapes. Oops. Well, anyways, you saw the 4-pin. So 4-pin has 2 rectangular shapes and 2 triangle shapes. This is kind of inspired by you have a power plug. It can be to have a 3-pin or 4-pin of different shapes, but we can do that. So we have done this kind of assembly for different parts, different shapes. Successful assembly can always be accomplished in this way in 10 to 20 seconds, even when uncertainty is 10 times of the task tolerance. In our task cases, we have the task tolerance 0.86 degrees in orientation and less than 1.5 millimeters in position. And the same successful performance can be accomplished in repeated runs of the same task case. It's very deterministic. And the method is general to assembly of parts of arbitrary geometry, arbitrary shape. Doesn't have to be pegging hole. It's just anything with rich contact situations and tight tolerance, and this method can accomplish. So now I'd like to talk about something different, autonomous object modeling and recognition. In my group, we're more applied. So I hear some very interesting, great ideas for more discovery kind of research, but this is kind of more always originated from some practical need. So we often need to have appearance-based 3D object modeling, and we want to, for recognition purpose, for manipulation purpose. The common approaches can be of two types. Either you have a fixed camera and then some turntable, put the object on it and turning around to show the faces of the objects, or some manual intervention, or a fixed object, then a moving camera. That can be more autonomous action, but view planning. But the first type of approach can be tedious because of human intervention. And the second type of approach may not result in the complete model because the object has to be changed in order to some pose in order to capture all the faces. So we use the autonomous approach of interleaving perception and manipulation in the process. So this shows just some setting. We have a fixed camera, RGBD camera, an object, and a robot manipulator. So the very simple approach is to take an image, build a partial model, and then push the object, so interleave perception and action, push the object to expose more surface to the camera, and grow the partial model, and so on, until some 360 degrees are reached. And then the approach checks for termination condition has all the surfaces being captured. If not, then change the so-called support surface of the object by manipulation and do the same process again. Okay, so for the object modeling, the 3D object modeling, we use the two adjacent RGBD images with sufficient overlapping of the scene, and to do a pairwise image registration using the feature A-shift from the vision, and also ICP algorithm to do that. So I think yeah. And then for after a loop is closed, we use a global optimization to further eliminate the accumulated errors and inaccuracies in pairwise registration. So this is an example. We have just a milk container. This is the very first image and the first model, and the robot started to push. So when we think about manipulation, we always want to think of something simpler for robot to do. Pushing is inherently much more stable. And this method doesn't really care if the push is a pure rotation or not. It doesn't matter, as long as we have the image and overlapping scene image in adjacent images, right? So it's a very tolerant of motion accuracies or uncertainty. And this is the view 18 now, and this is the current model. And finally, this is view 19, 360 degrees accomplished. And this is after the global optimization. So the manipulation is to find a new support surface. As you can see, we have different criteria for that. We want the new surface to make the object stable and also make it still easy, possible for manipulation. So in this particular case, the support surface is one opposite to the previous surface. And this is the final model. So this just shows some effect of a global optimization. Before the global optimization, you can see the accumulation of errors leading to some gaps here. But after the global optimization, those gaps are gone. And some other object model, just an image and the 3D model. So question is, that's a very engineered environment. We have the object there. and somebody still has to put the object there to the setting, and then the whole thing can be done automatically. What if the environment is cluttered? Okay, like in this case. So if we have, we use a continuum robot with a tip camera to try to model using the same method, basically what I described, but put it on a different robot with a moving camera, and to try to do a surface-based modeling of a target object. The surrounding objects are obstacles, something we don't care, but have to avoid, right? So here again, interleave perception and manipulation. With the first image, the robot already using that information to try to move to the motion of the continuum robot. Oh, by the way, this is a 3-section or 4-section continuum robot. We modeled this based on my collaborator Ian Walker's group at Clemson. They used the OCT-ARM continuum robot, pneumatic driven robot. Now we use that robot, we have the motion as either expand the curvature or actually reduce the curvature, expand the section, and then increase the curvature to have this curling effect. And this shows just a number of snapshots. As it moves, it sees more of the target object, but it also sees some obstacles. It doesn't try to model the obstacles, just try to, when it does real-time motion planning, to avoid obstacles doing this operation. So this shows that we have this robot that started moving. As it moves, what it sees on the upper left corner is what it sees in each image. So now it's a loop is closed. Now it's just a different object. This time it's a coffee container. It's larger. So the robot shape, when it's fully extended, still cannot wrap around this object, but it will use the other configuration, going to the other counterclockwise direction in order to cover the whole side surface of this object. What do you use for planning? The planning? Yes, for the robot. The planning is a kind of incremental, try to first move the tip camera to decide where the tip camera should be next. And the whole arm follows in inverse kinematics for this continuum robot. But also the motion has to be to avoid obstacles it detected. Yeah, so that's real time, but it's because it's incremental, it only needs to know what's the next. So kind of next view planning in this case, yeah. Okay, so this shows automatic object. Oh, I forgot to mention. So this, what you see is what you get. The total planning time is only like 20 milliseconds for the entire closed loop of the first example. For the second example, very similar. It's just one round is about that time. And okay, and the first one has about 11 images and enough to cover the whole side, to build the 3D side model. We didn't do the top and bottom in this case, but it's just something that can be done. We haven't done. So this whole little episode is about using this interleaving perception and manipulation based on RGBD sensing to do automatic object modeling. And the method is robust to robot pose and motion uncertainty because it's all image-based. Yeah.
The example with the continuum robot, was it also actually displacing the object while trying to model it, or was it only kind of looking around?
It looks, can you repeat the question again? It looks around object, you say what is?
Was it also displacing the object?
It's actually not displacing the object. So it's not touching the object. Using the image, it has kind of a normal direction and it just try to curve around the object to maintain certain distance. It's a constrained motion. It tries to maintain almost the same distance towards the surface.
Does it
Yes.
rely on getting that right? If it did make a collision with the object, would it still be able to correct for it, or would it be able to re-register?
It's not going to make a collision because it uses the camera to detect object. So it sees that within now and the next short distance, like 3 centimeters, there's no collision.
Exactly.
Yes. Okay. So it works for daily objects. And you can imagine if this kind of thing can be in a very confined space, and only you cannot see, only the robot can get in, and it's try to see what something in it, and try to use that to get model and to recognize the object. Now, what if RGBD sensing is not effective? This I have to say something to thank Chris Costas for your collaboration in this work. And I think it's a very cool idea. So Costas and also his former student Mabel worked with my students, and we kind of did that together. But the idea was initially actually posed by Costas. So what if RGB sensing is not effective? For example, for transparent objects or a very dark room, you don't have the vision. Can we still recognize objects? So the idea is that we use this kind of continuum robot to wrap around an unknown object and use the shape, robot shape, to encode the object shape. So effectively, action is perception. We don't directly use sensing, but we can use the robot shape, robot action, and the shape resulted from that as a means of classifying objects and recognizing objects. So we still use sensing a little bit. As shown here, we have this, this is a continuum robot. We have these sparsely placed, very simple touch sensors. But the touch sensors is only used for guiding the robot action for wrapping around object, not for perception itself. So the approach is we have touch-driven whole arm wrapping of the objects, and then the robot shape is described with the chord histogram. And next, we build a classifier from these robot shapes, a collection of robot shapes for each object. And then we do object recognition with active wrapping for unknown objects. So this shows the touch-driven whole arm wrapping. The wrapping has a very similar idea as what you show. It's extend the tip of the arm and then also change the curvature. So incrementally, and this time is guided by touch sensor. Okay, the touch sensor gives a simple signal of a normal contact force direction, and then the robot is just doing this type of wrapping around. Of course, this is the simulation, but later on I'll show you the real robot actions. So this shows the example wraps to encode object cross sections, all kinds of objects. And notice that the object shape and robot shape wrapping around object can be totally different. They don't have to look similar as long as they have a match, as long as we can use a number of those object robot shapes to classify an object category also in this case. So how to do that? We actually try to capture the 3D shape of the object by decomposing the workspace of the robot into different planes. And then for each plane, we can have a planar wrap around the 3D object. So we do that to cover the entire 3D space, if you like. So we represent arm as a set of chords, and each chord is 3D chord is represented by some 7 parameters: the length, chord angles, and also endpoint surface normals. So each blue line is a chord, and for a shape, there can be many such chords. So the object representation in this case is the set of chords of different wraps of the object put into a 7-dimensional histogram, and each dimension represents a parameter which is shown. And we use PCA to reduce the redundancy of the data. And in this case, just a support vector machine trained to classify objects based on chord histograms. So next, once the classifiers are done, the problem is, given an unknown object, how to conduct wrapping for recognition. Here we use the Markov decision process and the Monte Carlo tree search. The whole idea here is to balance the cost of incorrect recognition and cost of a robot movement of wrapping. So in this tree search, each node is a chord histogram of all the wraps observed so far. And starting from the first wrap, it decides how to add the edges as an arm movement to reach another wrap, and so to reach another state. And the search is to go through this whole tree to find the sequence of actions that minimize some combined cost function. In this case, the cost has 2 components. The movement cost, this is accumulation, actually average movement cost for the steps and divided by the number of steps, and also the cost of prediction. So it's a kind of a weighted sum of the cost. Now, some experimental results, I'll show you a little bit more real actions. With this method, we find that 10 wraps are usually sufficient for these daily objects, and 1,500 to 300 cores per object, 100 milliseconds to 1 second per wrap. And the classification has been performed for 185 objects from 10 categories, with the accuracy being 76% using the linear SVM. Obviously, a lot can be done to improve that, but this is just really the very initial work to show this kind of concept. So this is for recognition with active guidance. Each tree search is called an iteration. So the tree, how do you decide the size of the tree? The branching is kind of pre-decided, a branching factor, and the length is also, or depth is also pre-decided as a horizon search. Just say how many steps we want to look ahead before determining the next wrap movement. So that's defines the depth of the tree. And each iteration is an entire tree search, but there can be multiple iterations. So it's like a multiple tree search, or you can consider adding branches to the same tree to make the tree much bushier, and to just include increase the confidence level of the recognition. So here we have different iterations, predicted object and probability, and the number of wraps. And some example here: bottle, bowl, mug, and cup. You can see as the iteration goes, the prediction probabilities become stronger, but there are, of course, more wraps too. There's stronger prediction, but sometimes when we can get lucky, in this case, for the hammer, just 1 iteration or 2 wraps can decide give a very strong probability of recognition. So with my colleagues at the WPI, Chedashou now and his group, we used their real robot to do the real experiments. It's a 3-section robot and show the touch sensors and this transparent bottle object. And this is just wrapping of different objects. This is all just driven by the touch sensor. And box also in this case, but you can already see a little bit of a problem. I'll explain that. And the teapot. Okay, so we actually train the classifiers in simulation entirely, and then use the classifiers trained in simulation to apply to the real wraps. And this is so sim to real kind of transfer. And as you can see, for this bottle, and the prediction or recognition probability is pretty high and is correct, but this one is totally wrong. And this one is also correct. This is because for this box, actually one of the touch sensors was malfunctioning. So the robot didn't know it actually hit the object at that corner. It keep on deforming itself to wrap. So results in some shape. You look at this, the shape is very similar to the bottle shape. And that actually shows that for using shapes, one can increase the accuracy of recognition by more wrapping, right? And considering deformation or better sensors. It's just, we use extremely primitive, very sparse touch sensors here. So just some objects. Yeah, it is moving, and I'll show some real wrap here. And not just the wrap on the floor, but other kind of, we call spatial wrap, but it's other planar wrap, but kind of suspending the air. And these are for different, well, this is for the same object. And we can also see things for different objects. Yeah. Right.
The motor calibration of the robot, because you have to use somehow forward kinematics and then the positions of the test sensors or even just the joints, right? So how sensitive?
It's actually sensitive. I'll show you why. For the one that's if the wrapping is really just on the horizontal plane, it's not very sensitive, because we do have a way of calculating the shape. But look at the classification results. When we have a spatial wraps, the probability is it's become much worse. This is because of a gravity effect. So that when we do the simulation in classification for train the classifiers, we didn't consider the gravity effect of the real robot. And also the deformation effect is not considered. So the simulation to real transfer, a lot of the real world factor was not considered in the classifier. That affects the classification results. And also we didn't do enough. We could do more wrapping, but probably not enough wrapping in this real case. So that shows that a lot still can be done, but we have shown touch-driven wrapping of object for recognition through robot shapes after wrapping, and minimum use of touch sensing for guiding action, but not for recognition. So this is a great example that action itself is perception, not direct sensing. And applicable to object where RGBD sensing is not effective, but more work, definitely more work is needed to improve the robot, improve the sensing, and even learning, right? There are so many different kinds of learning methods now, deep learning, reinforcement learning, all kinds that could be considered. Okay, so now I'd like to briefly talk about real-time adaptive motion planning in uncertain environments. This actually is something that was first proposed by my student Van Nooy in as early as 2008. And then later my student Sterling McLeod applied to non-holonomic systems, and more recently Another student did it for constrained motion planning. The whole idea is the environment is very dynamic with dynamic obstacles that the robot doesn't know where the obstacles go and so on. So it has to do sensing, perception, and planning all at the same time in real time. So how can make the planning effective? This part is very different from all the other motion planning methods you probably have been more exposed to. The whole idea is we maintain a set of diverse trajectories. And then as the robot moves, all it does is to evolve those trajectories, kind of inspired by evolutionary computation, but re-rank to see which one is the best and constantly ready to switch to the best one to deal with the environment. So we call adaptive motion planning. So here's the idea. Robot, you can consider this as a configuration space. The robot is trying to move from a starting location to a goal location. This applies to all kinds of mobile manipulators, all kinds of robots. Okay, so as it moves, object moves, and it realized that the first trajectory it found is not good enough. It switched to the newly ranked good trajectory, and this good trajectory, you can see, is also different from the initial shape because it's constantly evolved by itself. And as the robot come here, it just switch. Of course, it can switch multiple times for this whole course of trying to reach the goal. And repeatedly, it does simultaneous sense, move, evolve, and switch to the better trajectories. But this is a very pretty toy-like example, but just to show the idea of what the robot sees and try to change its motion. It has no idea at all about this environment. Just use a little bit of a depth sensor and to guide its motion. So the blue robot and the person are all obstacles. And more recently, we considered task constraint real-time adaptive motion planning. So the difference is here, we have task constraint trajectories and also non-task constraint trajectory, all in the same population. The robot will have to switch based on the circumstances. Sometimes it has to release task constraint to avoid obstacles and sometimes it also recover. So this is a robot trying to move a cup of water without spilling the water. So that's the task constraint case. But then there's a dynamic obstacle and it has to avoid the obstacle. Sometimes it can avoid it while maintaining the task constraint. Sometimes it has to find an intermediate goal to put down and wait and also avoid obstacles until obstacle is away. Now it resumes its motion. You can consider this a robot waiter in a dynamic environment will have to do some of the maneuvers like this. And this is just a different example. So different task constraints. So the robot trying to push a drawer in, then find some obstacle. This is of course very simulation. It's a UAV, but just show the whole idea. The planner is exactly the same. We don't hard code anything. This is the planner use the detection to decide where it goes. Okay, so finally, I'll use maybe a couple minutes to talk a little bit about semantic SLAM in unknown environments. We know SLAM is for simultaneous localization mapping. Semantic SLAM, I'm sure Costas and others and working on a lot of semantic characterization of the environment, is to capture and map the semantic information, semantic objects in the map for SLAM. But related work either hardly consider the data association at the semantic level or some point representation. So it's a low level representation of semantic objects. And difficult to do real-time operations. So we considered a semantic SLAM method with autonomous object level data association. The whole idea is that we use some method like the ready YOLO v3 to identify objects in the scene with a 2D bounding box and the label. And then we fit that object with a quadric shape for 3D size and shape capturing, also with the position and orientation of the 3D objects. And we build this into the, register this as mapped objects. Now, when a new scene, new frame is considered, we do an association. We map the new object to all the mapped objects by semantic information, hierarchical matching first. So if the semantic information matches, we go to the geometrical information, like the representation of the shape, the location, and so on. And to find the corresponding candidate. So see, this object has been seen before or not, or it's a new object. So that's the whole idea about the data association. And this is the TOM, RGBD, FR1, XYZ sequence. And we just use that to try our algorithms. And YOLO v3 is used to detect object with the labels. And then we put the quadric to capture the shape. And you can see the labels from one frame to another. If the labels don't change, that shows they're seen objects. And this is real time. We also used 3D high-level semantic information for aiding loop closure. Loop closure detection can be a problem. Using low-level ORB SLAM 2 or ORB SLAM 3, a lot of times very similar scenes that are considered the same cannot differentiate the detail if the details look very similar. So we consider using a 3D semantic co-visibility graph of the semantic objects. Each node of a co-visibility graph is an object, semantic object, and we add an edge if two objects are observed together for 3 times. And we compare for each frame, we compare this co-visibility graph with the next frame to see if they really represent the same location, seen or not. So in this example, we have 2 apartment scenes. They look very similar. Actually, ORB SLAM 2 or ORB SLAM 3 could not recognize their differences. Consider that a loop is closed, but they are different apartments in different floors. And we use a high-level semantic co-visibility graphs. We can, our method successfully detect the differences. Okay, I think my time is up almost. So just to summarize, I've introduced a bit of a research in these 4 areas. Of course, in each area, more research can be done and more interesting things can be explored. But also interesting thing is to see the connections of them, right? We see a lot of SLAM work or real-time planning work, but SLAM and real-time planning really should be combined in order for the robot to be really successful. And it's not just about mobile robot. It's about manipulation, manipulators, and so on. And object modeling and robotic assembly. This can also go hands in hands. Assembly is not just in the industrial setting. We have a lot of daily life assembly. Just put things together in a very tight clearance tolerance requires the handling of these strategies and so on. So just these are the students involved in the research I presented and the collaborators, including, of course, Kostas here and Mabel. I still really appreciate the whole idea. I think this was so cool. And some ongoing work, I have students doing constraint continuous coverage motion for free-form surfaces, for robot code spraying or painting. It was really very applied problems at the motivations. But then we discovered, or under task manipulator constraint. Then we discarded freeform surface representation, a very good one for robot path planning. With manipulator is not really there. We also feasibility study, given a robot, given a surface, you have a lot of parameters, where to place robot, where to place surface, and the joint constraints and task constraints, do they all match? Can we do a continuous coverage of the whole thing or have to divide it? So feasibility study. And finally, coverage motion pattern path optimization. So we've done some work in that. And also a student have been working on the autonomous exploration of unknown structure for 3D reconstruction. That's really a combination of traveling salesman's problem, art gallery problem, and SLAM. And this shows just a scope of things. And he put a lot of effort, try to build an efficient data structure or management structure for all the data in this kind of a process. This is also ongoing. A human, really a huge effort. Okay, so that's it for my talk. Thank you very much.
All right, thanks, Jing. That was amazing in terms of the breadth, from my point of view. So the next section, we'll have a panelist. So I will be moderating the online, and we've got Leon Kim from Michael Pozo's group. He's a PhD student in his second year. He will be handling the in-person questions. So also, if you're in person, don't forget that we need to hand you the mic so that the online people can hear. And if you're online, don't put in chat. Please use the Q&A button, and we'll go from there. So Leon, we'll start with the first question.
Sure. Thank you, Jing. I just wanted to thank you for the wonderful talk. I thought it was very interesting. And I wanted to ask first a very quick clarification question. This is really directed at the first work that you presented. So I just wanted to make sure I understood. You only take a single sample of the force measurement for your task. Is that correct?
Well, actually, it's not just a single sample. We wait a little bit. So the force sensing just continuously doing, right? We kind of average a little bit. Not just, I mean, it's hard to say what is a single sample. If you have the contact, you stay there. Then because of uncertainty, the numbers can change, but we kind of used a little, but we didn't use any filter or anything like that. We could, but
yeah. I was wondering, I can imagine just, I guess, from a single, I guess, average measurement, let's say, there might be non-informative contexts that are possible where you have multiple potential pose corrections that explain the same sort of sensed force. And I'm wondering if you explored like a window, let's say, of and somehow like match the pose to explain like that window of force samples rather than just like a single snapshot or maybe just average.
Yeah, a little bit average. But what you just mentioned is very correct. You can have the same force torque sensing data for very different context states. So in this case, that's why sometimes we predicted contact state, the forces will match, but it doesn't lead to successful insertion. So we realized that, I mean, the system realized that and do another prediction or another prediction, but usually twice we will get there. In all the examples, it seems like just two kinds of contact states give you exactly the same, well, not exactly same, but very similar sense force and torque.
And I have one really quick follow-up question to that. And I was wondering, like in this perception action pipeline, it seems a little bit one directional where the perception is mostly informing the action and then it sort of just replans. But I'm wondering if you explored more like direct coupling between the perception and action where the policy actually tries to take additional actions to explicitly disambiguate these like ambiguous like context scenarios.
Yeah, actually a lot of this is, especially the assembly situation, is more action to disambiguate situation. Sometimes when we just have one contact state, the prediction is incorrect, then the action shows that, right? So we have a different prediction, or inaction shows that. Or sometimes the prediction incorrect and the robot can move actually, can still try to go to the goal, and then it leads to another incorrect configuration. At this time, the newly sensed force can accurately match this new configuration, and then we can be successful. So the action is helping to disambiguate situations.
Thank you so much. I guess Mark will switch off.
The first online. Okay, thanks. First online question, maybe it's two questions. How can we handle objects that require more involved interaction to gather about, such as articulated objects? And then related to that, would it make sense to use some recent advances in neural implicit representations like deep SDF, NERF, et cetera, to instantiate the object models on?
I think that makes sense. Yeah, you mean this is also the assembly problem, right? Is that about assembly problem? Yeah. Now, if you have articulate object, we actually years ago, we had work on classifying all kinds of, characterizing all kinds of context states with articulated object. It's certainly the dimensionality goes up a lot. So yeah, we haven't explored this, but more learning can help with this, yeah. Okay.
Thank you very much for the talk, Jing. This is actually also about the first part, so maybe it's a good time to ask that question. So I think what you were doing, if I understood correctly, was you were using simulated contact forces to verify your hypothesis about the object pose, right? But this typically tends to have some, it's hard to be kind of fidel to the real world, right? To have high fidelity to the real world. And I think you mentioned briefly that you kind of did something to correct for this, but I didn't quite catch it. And I was wondering if you would be able to talk about it for a little bit.
Yeah, very good question. Yeah, I said we have the calibration. We have the computed force, and we do a calibration to be the force more in line with the real sensed force. And this calibration model is learned. But it's not a super complicated or deep neural network. It's a simple neural network, just feed forward. Because we just collect some force data, and then the real force data and match to our computed force data, and then it worked very well by just a few thousand data, and some for training, for some testing, but the results is surprisingly good. I think because it's what is learned is very simple. It's not so complicated. It's just matching these two forces. So we call it calibrator.
Great results also from the last 3 years. In the loop closing, is it just statistics of pairs of co-visible objects, or is it like a graph matching?
Graph matching.
It is graph matching where you and the graph you're building is from the visible objects locally. Okay, while you still keep a graph of the whole environment.
Because we don't know, because this is SLAM, right? If we're semantic SLAM means exploring new environment, you can have new objects, but we don't know if this is a new environment or old environment.
Right. Mm-hmm.
That's right, yeah.
I wanted to ask a question about how we go about interacting with an object that might fall for something. And it's I want to generalize the question a little bit. So if you have, let's say, a wheeled robot that would like to go through grass, this is a situation where you do not have percepts and you're exploring the object, and maybe there is a ditch and you fall down. So what do we learn by, or how should we interact with objects when we do not know what will happen if we interact a tiny bit worse?
Okay, how to interact the object with, do you talk about this touch-based wrapping object?
Yes. So
How to interact with the object
yes.
when you don't know anything, right?
When you're really probing the system to push, to try going closer and closer to the limit, right? For you in interaction, it is about grasp or touching a bottle that does not have too much weight that could fall. You can think of other situations where we are parking a car in a new spot.
Yeah, it's a good question. So far we haven't considered what if the bottle is just like this or something like that. We haven't considered that, but that's why this is just the beginning. There's so many things can consider, and also you can. So this is, yeah, this is a very good question. I think then we still, I don't know if this is like that. I don't have any other sensors. It's tough. It has to have some sensor. Maybe we can do an exploration. We can say if we do an exploration to kind of try to capture this as a different situation, we can anticipate, right, different falling scenarios and try to capture them, even classify them. Then that can handle it. But yeah, and also another interesting thing is interaction can make you recognize this kind of wrapping can really make the robot recognize something other than the shape. Like this is softness, right? Is this a full bottle or half or empty? By squeezing further, then the robot deforms more. If we capture the deformation, that can be used to recognize this type of characteristics or characterize, yeah, recognize these kind of characteristics. Yeah.
Like Mark, I'm also very impressed by the breadth of the research you presented. And so I'd like to ask you about the proposed combinations of some of the branches that you presented and what you think combining those areas of research might look like in terms of next demos, for instance. So particularly in the model building projects and the autonomous assembly projects, what do you think you might be able to accomplish by trying to assemble objects that are new and you may have to model them first? What do you think demonstrations might look like that build upon both of those areas?
Yeah. Oh, great question. We can, if we have some parts for assembly, we don't have the CAD model anywhere because this is just a daily object, right? We can use our modeling method to capture a model, a point cloud model, something like that. Okay, and that model can be converted to a mesh model or our sphere tree model. These conversions can be done actually automatically too. And once these models are there, and our assembly method can be applied. And notice that we don't consider a fixture or things like that because we can handle the uncertainty. And we can combine vision. Right now, we're only focused on using the force for dealing with contact situation. But the gross motion, when you have something, you can use vision easily, right? To move the robot to your newly captured objects. And maybe grasping if needed and grasp. And then this method for force guided assembly can be done. So this is, yeah, okay.
How do you envision figuring out how two novel objects assemble together? That seems difficult in my opinion, but maybe you see some ways that it could either be simplified or ways to make this task easier.
Once we have the models, I think we'll have to have more knowledge, right? The models may be new for the robot because it doesn't have an internal model for this object, but the objects like we have all kinds of object detection methods says this is a cup and you put a cap on it, and then what the normal assembly motion should be is known. So these can be captured. We also consider human robot interaction in this case, because if we have, say, if a very flexible environment to have a robot doing all kinds of assembly, all kinds of things, then how to change things, we do need some people there. And ABB has this Yumi robot. I have one in my lab for this purpose, for the human and robot work together for, say, assembly. And so what the person should do, I think this is actually could relate to Professor Jianbo Shi's research, better for a person to help, what should be the autonomous automation part. So we've just recently got a Army grant for human robot interaction kind of interface evaluation, and we want to use this assembly type of manipulation as a task case for this kind of a study.
So for modeling shapes for kind of shape reconstruction and shape classification with the continuum robot, I think you were doing both the reconstruction and the classification, but if I remember right, for classification, you weren't really using the output kind of shape estimate as the input for classification. You were instead kind of constructing this feature based on a histogram of chord lengths, I think.
Yeah, that's
Could you speak about why that was a good choice for the classification task? Would it not have been kind of the obvious thing to do to like take the shape reconstruction, for example, or something like this? Was that kind of a less informative estimate?
It's actually simpler, right? Because chord is just a straight line. So even for the straight line, we have some 7 parameters necessary to explain it, because it has a position parameters and the length parameter. And if we try to capture all different shapes of the robot, we'll use more parameters.
It's okay. Yeah.
So that was, I just have a kind of quick follow-up question to one of them. I was just thinking about a demo that could be kind of interesting. Let's say you have a vase that falls apart or is broken. Could you use, the detection modeling method to see what the parts are, and then somehow figure out like where the pieces should go, and then have the assembly pieces put it back together again from a completely unknown.
Yeah, that's a great suggestion. Oops, that's a great suggestion. We should try it, because if you know what is the shape of the assembled part, and then break it down and say assemble it back. So I think that can be a fun one. Great demo to do. It will be great. Yeah, and also I think I didn't answer your next question. You say how to do this connection, right? You say one example connection. Another connection we're trying to do is the semantic SLAM and task level planning. Lots of task level planning approaches, but hardly, combined with this mapping and localization. People tend to assume everywhere robot is known somehow, right? Very accurate localization, but is that the case? It's not if in a real environment.
All right, let's thank our speaker one more time. That was fantastic.